All right, so we're talking about section 4.1 now. Whoops, change the color of that. Let me erase that. So 4.1 in the text is about how to put an LP in what we're going to call standard form. So what do we mean by standard form? Standard form is anything of the form max or min, because they're equivalent. C transpose times x, so the maximum is taken over x, so the c's are the constants, right? And so just to give you fair warning here, right, this is a dot product, so this is a scalar value. The c transpose x is a scalar value, right? So we're maximizing that quantity over all possible values of x such that ax equal b. But there's some extras. We want x to be greater than or equal to 0, and we want b to be greater than or equal to 0. Okay? And like I said, this could also be min. Okay? So, just as an example, let's convert minimum problem, minimum 3x1 minus 4x2, such that minus 2x1 plus x2 is less than or equal to 1. Oops. Minus x1 plus 2x2 is greater than or equal to 5. And x1 plus x2 is less than or equal to 7. With x1 being greater than or equal to 0 and x2 being unrestricted in sign. Good. So there are several issues here that we have to take care of. Issue 1 will be the max min. Then we need all of these equations to become equalities. So we're going to treat less than or equal to's as different. So these are going to be issue 2 than the greater than or equal to. So that'll be issue 3 that we'll discuss. And then issue 4 is this unrestricted in sign issue, right? Good. So let's see. So to convert, by the way, the secret here is in 2 and 3 that we're just going to introduce new variables. Actually 2, 3, and 4. So we're introducing a lot of new free variables. Good. Now, I should say for issue 1, converting the max to a min, you don't have to, but I think it's better just to be consistent in everything that we do is just to say that the minimum of 3x minus or 3x1 minus 4x2 over all possible x is equal to the maximum of minus 3x1 plus 4x2, right? So I'm taking the negative of my function. Okay, and so my new function will be minus 3x1 plus 4x2. Good. 2 for minus, oops, let me write down the constraint again up there, less than or equal to 1. We're going to change that, and we're going to change that by introducing a new variable. Let s1 be greater than or equal to 0. S represents what we're going to call slack. That's why we're using the letter S. Okay, and so we're going to redefine it then. Minus 2x1 plus x2 plus s1 is going to be equal to 1. So that really defines s1, right? s1 is defined in terms of x1 and x2. Good. Now the same thing is going to happen to constraint 3. If we have x1 plus x2 less than or equal to 7, let s2 be greater than or equal to 0. Again, S represents slack. So then I'm going to rewrite x1 plus x2 plus s2. I'm going to leave a space there for s1 because later on we're going to, well, I don't need to do that right now, I guess. Plus s2 equals 7. Good. Finally, number 3 is what? we want to use the equation minus x1 plus 2x2 greater than or equal to 5. We need to do something to that. So the idea here is we're going to let e1 be greater than or equal to 0, and e is going to represent excess. So e1 is going to represent the excess of this quantity to 5. So we'll write x minus x1, jeez, did I just do that? Minus x1 plus 2x2 minus e1 is equal to 5. Now why is that minus there, right? Because e1 is going to be the excess between this side and this side. So another way you could think of it is minus x1 plus 2x2 is equal to 5 plus e1, right? And then I'm bringing the e1 over to the other side. So that's another way to think about why that's minus. Okay, and so that was issue 3 in our list. And finally, issue 4 in our list was the unrestricted and sign variable. And so in that case, in unrestricted and sign, let's see, how many variables do I have right now? I've got x1, x2, that's my unrestricted and sign, but then I've got s1, s2, and e1. I just want to keep track of everything. So what I'm going to do is I'm going to introduce x3 and x4. And the way I'm going to do this is I'm going to take x2 and I'm going to say let x2 be equal to x3 minus x4. And the reason I'm doing this is because now x3 and x4 can be forced to be, I should say with, x3 and x4 can be forced to be greater than or equal to 0. So in that case, do you see what happens? If x2 is a negative number, we can take x3 to be 0 and x4 would be that number. And then if x2 is a positive number, you can just take x4 to be 0 in our solution. Good. And so what we end up with then is our new variable set. The variables are now x1, x3, x4, s1, s2, and e1. Good. So we've got a lot of new variables. And so here I go. Let's start off with our equation or set of equations here and rewrite it so that it's in standard form. Okay, so now we have max. Now remember, I've got a bunch of new variables up here. So it was going to be minus 3x1 plus 4x2, but in place of in place of x2, right, I'm going to have x3 minus x4. And then just for clarity here, this is going to be plus 0 s1 plus 0 s2 plus 0 e1, right? Oops, you know, I should put these in order of appearance. e1 plus 0, whoops, 0 s2. Very good. Such that minus 2x1 plus x2, which is x3 minus x4, plus our s1 equals 1. My headphones are falling off. Minus x1 plus 2x2, so that's going to be 2x3 minus 2x4 plus 0s1 plus 0, oh, wait a minute, this is our excess variable, that's minus e1 equals 5. And then our last one, x1 plus x2, which is x3 minus x4, plus s2 is equal to 7, I guess. Good. And now x1, x3, x4, s1, e1, s2 are greater than or equal to 0. And the idea here is that in the theory that we're going to talk about, you know, when we talk about the LP in standard form, in the original problem, you know, our variable set x was in R2, right? But what we've just done is we've increased the dimension, and so standard form, Our new variable set is in R1, 2, 3, 4, 5, 6. Okay, and so this is where we're going to be. We're going to be in the higher dimensional set. Good. That was a fast 10 minutes. So that was an example of how to put a linear program in standard form.